Hi guys, my name is Rushang and today I'll be presenting our work on relational abstractions for generalized reinforcement learning on symbolic problems. This is joint work with Siddharth Srivastava from Arizona State University. Let me start off with a motivating example of the logistics domain, which is also known as the package delivery domain, in which you have a bunch of trucks, a bunch of cities, and a bunch of packages, and the objective is to deliver packages to the respective destinations. Now, because of the nature of the roads and transportation, failures could happen, so it's a stochastic world out there. And most of the modern packaging companies, like FedEx, etc., store all this information for solving this problem in the form of databases, like the ones on the slide, where you have the driver information table, which contains records about the driver information, like the license plate, the name, and the designation, and similar. Now, converting this tabular data into image-based representations is not that easy and intuitive. And as a result, many of the existing DRL works in the literature are not going to work because they mainly assume the existence of image-based data as input. However, these relational databases can easily be converted into relational representations, and I'll go about that more in the next slide. So, to briefly talk about a problem setting, we focus on RL for MDPs, where the action dynamics and the reward function are implemented by simulators. And instead of image-based states, now we have relational states and actions. So states are defined as sets of predicates. So if you want to describe that the truck is at Tempe, or the truck 1, you would just say a predicate truck at Tempe, truck 1 at Tempe. So the need for generalization in these problems is pretty important because RL techniques like Q-learning are not going to scale as the state spaces grow exponentially as the total number of state variables increase. So one tractable solution is generalized policies, which transfer to a class of problems for a domain. As an example, for logistics, one policy can be go to the nearest location with an undelivered package and then simply make a beeline to deliver it. This usually yields a much higher reward than a random policy. It can easily be computed from very small examples with a few packages, and it transfers to problems with an arbitrary number of packages and locations. So, because it's so important to compute these generalized policies, there's a ton of related work in the area. For example, MBRRL computes generalized policies using conjunctive first order features, but it requires expert hand-coded contextual information. So, our contribution in this work is a neuro-symbolic approach to generalization, where we use abstraction in conjunction with deep learning to learn a generalizable relational Q function that expresses such a generalized policy. And we train our network in a data-efficient fashion using leapfrogging. So, what's abstraction in our approach? So we define a bunch of features and feature kernels that can capture high-level information about states. For example, for logistics, a feature could be to set the packages that are not at their destinations. And the feature kernel would simply look at the state and compute, okay, which packages are not at their destinations. And it's easy to see that this is capturing high-level information, and if you take the set cardinality of this feature kernel, you can lift problem-specific names and numbers. And regenerates this feature set automatically without requiring any human input. In fact, for our approach, there is no human input at any point in the process. The next step, once we have a fixed size feature list, it's easy to use deep learning because now we can use multi-layer perceptrons to do the learning for us. And we can train our network, which we call QGRL, using deep learning. One problem with GNNs has been limited in expressivity, which is why our choice of using MLPs, because features that we use are more expressive. Finally, we scale up transfer by using a technique from a prior work called leapfrogging, which is basically an iterative, automatic curriculum-guided self-training technique in which we simply have an iterative cycle of transfer and then learning on small problems that can improve the generalization capabilities of our networks. So, for our empirical evaluation, we use 4 tasks from the IPPC, which is the International Probabilistic Planning Competition. Our baseline, I spoke about MBRRL before. It uses conjunctive first order features, but it requires hand-coded contextual information for good performance. We also compare with SymNet, which is a GNN-based approach. However, the problem with SymNet is that even though it offers good performance, it requires access to closed-form action models, and thus is not directly applicable in RL settings, even though it's trained using RL. So, going over the results for across the 4 domains, I do want to point out that to showcase generalizability, the minimum sizes of the state spaces in our test problems were much larger than the problems we use for training. As you can see from sysadmin, the minimum size of the state space in the training problem was only 2 power 6, but the minimum size of the test problem was 2 power 30. We can see that in terms of zero-shot transfer performance, our approach, which is the green bar, is able to outperform the baseline in almost all the domains. Similarly, in SimNet, we are not able to outperform SimNet, but we are able to remain competitive, which shows that GRL can make up for the lack of availability of action models compared to approaches that do use additional information like action models. So, in summary, in this paper, we introduced a new approach that uses description logic-based abstractions for generalized reinforcement learning, and we scale up the transfer by training our networks using leapfrogging. Our results do show that our approach facilitates efficient zero-shot transfer. And please do stop by the poster session today for a detailed discussion, and you can email me or scan the paper, and thank you.